Good to start. Yeah, right now it's already 3 minutes past the hour. All right, go ahead, Bob and Mihalo. Yeah.
Uh, okay, good morning, good afternoon, good evening, everybody, wherever your time zone happens to be. This session is going to switch gears a little bit from some of the earlier sessions we had on this track. We're going to be talking about some data warehousing techniques. My name is Bob Carlin, and my co-presenter who will be doing actually most of the work as Mihalo Tekic, and we're going to be talking about extreme techniques for data warehousing. So we're often asked, what is real-world performance? We like to think that this is, it's really just two things. It's getting the most out of both the software and hardware that you've procured and achieving excellent performance. Those are really the two key things that we kind of stand by when we're doing customer engagements. Now this may be a bit of a recap for any of you who have seen some of the earlier sessions, but for the new people on this session here, just who we are. We're actually part of the Oracle database development team, although we don't actually own any of the code, which means that we don't have any sort of bias to any one particular piece of code or feature or product, which means we can remain sort of neutral in that respect. We have, although we're actually a very small group, but we do have team members across the world, across USA, Europe, and Asia, and we have literally hundreds of years of experience combined within the team. And in fact, I think just with the members, just with the presenters here this morning, we probably have well over 100 years of experience. So it's a very experienced team. How we work, we have a few kind of like key mantras that we live by. Use the product as designed. Take a holistic view. You know, look top down at performance. Aim for best performance and not good enough. We like to apply data-driven analysis. So it's all about taking the guesswork out of performance problems and using the numbers to tell us where performance problems are. And then once we've done all that, we share what we've learned, and that can be sharing with you know, the greater Oracle community in sessions like this. We also offer training classes, and also we share what we learn with our internal Oracle development teams so that we can, you know, improve the quality of our own products. We really kind of have three things that we do in real world performance. We do customer engagements. That means doing sort of performance reviews or escalations or projects where we get involved with design and build and of high performance, high scaling products. Although I said we didn't do database development, we do build sort of tools and utilities within our group to help us perform data analysis and triaging and that type of thing, and we share that with people too. And then, as I mentioned earlier, we do customer education. You know, that traditionally has been in person, face to face, but you know, in this brave new world, we're now offering those classes online as well. Okay. In terms of actual engineering, one of the key things that we try to do is to get to the root cause of database performance problems, and we really see these kind of breaking down into three areas. One, the database is not being used the way it was designed to be used, the proverbial square peg in the round hole. The second is that the application is suboptimal in the way that it interacts with the database. You know, a good example of that might be something that constantly logs on, logs off to the database, or does a high amount of parsing, something like that. And the third could be that there's actually a suboptimal algorithm, which is a euphemism for a bug, in the database. And then we have to take the approach of what can we do to help the customer to avoid the bug, and what can we do with our development teams to get these bugs addressed in the most efficient way. Okay, so let's just switch gears now to database performance specifically. And over the last decade, we as Oracle has greatly increased our capabilities in the data warehousing space in terms of what we offer from both a product perspective and a hardware perspective. So talking about things like the Exadata storage system, database in memory, where we're able to do things like vector processing, smart scans, Bloom filtering, storage index, all these types of things, all things that come to bear to improve performance from a data warehousing perspective. However, what we have found is that a lot of existing and older data warehousing projects have been built with an OLTP mindset to things, where the idea is that the only way to improve the performance of a query is to add an index, or to increase the scalability is to run more threads of the same thing. So what we try to do is to kind of educate our customers and people who try to do these projects in some of these data warehousing concepts, so they understand things like I/O bandwidth for the storage, parallel processing, set-based techniques. All of these kinds of things go into making a successful data warehouse project. Now, one of the key elements of a successful data warehouse is actually the data model itself. And there's a lot of literature out there that explain this idea of a star schema, where you have a fact table surrounded by dimensions. Conceptually, it's a very easy model to understand. In practice, actually designing it and putting it together does take a certain amount of skill from a data modeling point of view. But the idea is that this star schema, which is what we aim for, or some sort of derivative of it, such as a snowflake schema, where you have multiple dimensions or hierarchies of dimensions. It's a very well understood design pattern out there in the real world. It's actually proven to scale really well, and it's designed and works well with third-party query tools such as MicroStrategy or Tableau, or any of these tools that I use that understand the idea of a dimensional model in order to build the queries for you. So what we're going to do today is actually take a look at so this is kind of one of our sort of day in the life sort of presentations, where what we've done is taken a real world scenario that we've seen actually several times in dealing with customers, and we're going to sort of present this in a how we did the analysis and how to understand the problem that we faced. So this is basically the query and the model that we're going to deal with in the rest of the presentation. So it's basically a snowflake data model. So it has a hierarchy, and then we have a SQL statement that we have built here. Fairly simple SQL statement, typical dimensional query that we're going to run against this particular schema. Now, one of the advantages of the dimensional model is that it's very predictable. Knowing the data model and looking at the query, you can pretty much come up with the execution plan. At least in your mind, you can come up with the desired execution plan. And also knowing the data sizes, the number of rows in a table, you can get a good feel for how long you would expect the query to run. Certainly from a data acquisition phase, because we know how long it can take to scan each of these tables given the speeds and feeds of the hardware. So for this particular query, we would expect it to return the results in 10 seconds or less. So this is the desired execution plan that we would expect from that type of query. But let's see what's actually happening when we run it. Well, when we run it, we find that it doesn't take the 10 seconds or less that we would expect. So what do we do to address that? Well, there could be a number of things that we do. Do we update the statistics? Do we build histograms? Do we create column groups? Do we increase the degree of parallelism? Do we set optimizer index cost adjust? Do we set cursor sharing to force? Do we increase the block size? Do we go onto the internet and look for some magic hidden parameter? Well, the answer is no, we don't do any of these things, because at this point, all we're doing is guessing. And I like to take a quote from somebody who had the ultimate in performance problem. Gene Kranz, the flight director of Apollo 13, said when the explosion happened that let's work the problem, people. Let's not make things worse by guessing. And so that's one thing I always encourage my engineers, is to find out why something is performing poorly and just guess. You could get lucky and you come up with the right solution by guessing, but that's not engineering, that's guesswork. And I like my guys to be engineers. So just to recap, here is the schema and SQL statement that we're working on. And at this point, I'm going to hand the screen over to Mihailo Tečik, and he will take you through the demo of the analysis phase of addressing this problem. Mihailo?
Yeah, first I need to unmute myself. And can you stop sharing? Okay, good. Let me share my screen now. All right, so right, so here is a query that we are going to work with. You know, as with any performance problem, we want to take a good baseline of our query. So when it comes to analyzing performance of slowly performing queries or SQL statements, the tool of choice should be SQL Monitor. So I'm going to use, in this case, DB Express, or you can use Enterprise Manager, and we are going to just move this window here. Okay, we are going to see what the execution is doing and how the execution is performing, right? So this is going to run slightly faster, I'm expecting, in the interest of time than the 1.5 minutes that you saw in the slide. It should complete around 1 minute. But let's take a look into SQL Monitor and see the execution so far. So I'm going to collapse. Actually, as you can see here, we're using degree of parallelism 4. This is a parallel query. I'm going to collapse this part. I hope by now you have seen SQL Monitor and have worked with some. But for those that don't have so much experience in analyzing, doing performance analysis of a SQL statement, typically what we'd like to do is to understand where our execution or database time is being spent during this execution. And probably the best place to look at or to start with would be the activity tab of a SQL Monitor. The activity tab will tell you which row source operation in particular is responsible for most of the database time being spent. And as you can see here, it is a row source operation 43, which is table access by index row ID on products table. Now, this is a table lookup, which indicates that the data in products table is being accessed through an index. Right? And if you look a little bit higher to see which row source actually uses that particular row source operation, you will see that would be these nested loop joins here. Okay, so at this moment, you know where the time is being spent during this execution, 70%. And again, this is not even completed. Let me see if it completed. Yeah, it completed, 77 seconds. It's slower than I hoped. Right, so let me go actually back and refresh this and get a completed SQL monitor. Here we go. Oh, this is still the running one. I need to first try DB Express for some reason. Okay, so this is the completed one, and as you can see, we're performing, about 17 million, scans of the index, and then to return 16 million rows back, right? So why did the optimizer came up with nested loop joins? Well, the optimizer thought that there will be 29,000 rows returned, from this particular hash join at row source 9, right? However, the reality is it returns 16 million, right? So over here, you can say, well, is that right? Well, if you have an index in place, it does some cost calculations and says, well, if I have to traverse 29,000 times and there is an index in place, I'll go and I'll opt out to go with nested loop joins instead of a hash join, right? But that's just the decision the optimizer made based on this particular estimate. Now we need to understand why the optimizer ended up with this underestimate. One thing that we typically mention to the customers is that the vast majority of the slowly performing SQL statements are performing poorly because of large cardinality misestimates, which will make the optimizer to flip between an optimal desired, let's say, join method or access method, and go to suboptimal one, right? So in order to figure out where the problem is, we really need to understand what happened before, where this underestimate of 29,000 compared to 16 million occurred first. Well, if you look into that, and if you look into the hash join that supplied data, produced data for this nested loop join, you will see that that hash join actually is, we have another hash join here where we are, let me just collapse this really quickly, right? We are joining a result from some, well, first we are joining result from some data set to suppliers. When we see suppliers, cardinality estimates, they are quite good. So we have 1 million rows, 1 million rows. We are not worried about this. So we go on the side, of the left side of the join, or the probe side that has the same join cardinality underestimate. And as you can see here, on the left side of the probe side, we have estimate of 10, but the actual cardinality is 6. Let me just go here so you can see this is the actual cardinality is 6,000. On the right side, actually was the build side. On the probe side, we have estimate of 147 million rows, and the actual is 19 million. Well, this may look like an overestimate, but actually it is not. The reason why you have less actual rows is because the Bloom filters kicked in, and we actually pre-filtered some data by doing sparse scan. So really, what I want to look at now is why did we end up with this large cardinality underestimate for this particular row source? And now I need to drill in a bit deeper to understand where, for the first time, I see big cardinality underestimate. And if you go and look at, you can see that this hash join here, we have cardinality estimate of 1. The actual cardinality estimate is 150. Okay, so that's typically a red flag. Actually, always when you see cardinality estimate of 1, it's kind of a red flag. It might be correct, but sometimes it may not. And if it's not, then the optimizer may take different routes. In some cases, even going with a Cartesian join. And if you instead of 1 have like millions of rows, you have a problem. So here we have locations, right? For locations, we estimate the cardinality of 3, and the actual here reported is 240. Well, it's not 240. In fact, it's 60. Why is 240? Because here, we are using what we call small table replication, which is similar kind of sort of distribution method like a broadcast, where each of the PX servers that are going to perform the join that are on the receiving side are going to get a copy of locations table. So because we have 4 times 60 is 4 times 60 to 40. So again, we have estimate of 3 and actual cardinality of 60. Now we need to understand, what is going on here? Why did the optimizer come up with an estimate of 3? Well, in order to understand that, we need to see, what kind of filters were applied to this particular table. So the optimizer comes up with this cardinality underestimate, the single table cardinality underestimate. So if we click, and again, this is the new version of SQL Monitor. In the old Flash version, you will go in the Plan tab, and I think that's what we have in the slides. But here, if you click, you can see that the filters that we applied. So we have CT equals CT1, or CT equals CT4, or CT equals CT5. So based on that filter, the optimizer said, well, I think there will be only 3 rows returned. Now we would like to understand a bit better how the optimizer came up with that information. Okay, in order to do that, we need to understand the data we are working with. So I'm going to skip to SQL Developer now and check some stats. Let me just move this part with the, okay, the zoom thing. All right, so what I'd like to know at this point is, well, how many rows I have in locations table? In locations table, in this case, we have about 100, we have about exactly 100,000 rows. Now, the next thing that I'd like to understand, again, remember, here we're trying to figure out why the optimizer came up with underestimate for single table cardinality filter. So we'd like to understand the distribution of the columns of the data for the columns that we are using in our filter, which was city. So if we run, this query where we check the number of distinct values, where we have histogram, where we have any nulls, what we can see is that we have about 98,000 distinct values for cities. So there are locations that are spread across 98,000 cities. Obviously, some cities have multiple locations that they have, recorded or they have in their database. And we have a histogram with 254 buckets. All right. So if you have a histogram, we would say, well, you know what? I would expect to have, buckets for the values that I am looking for in my histogram, right? And if you don't have that, then what will happen is that the optimizer will use, typically if you don't have a match, it will use some heuristic, which is, it will find the bucket with the smallest value, the smallest size, and it will use some heuristic. It's about 50% of that size to use a selectivity or cardinality for that particular filter. In this case, it can be very low. Actually, it's lower than 1, but it runs it to 1. And since we have 3 filters here, 3 values, we end up with cardinality of 3. Now, the good thing is this is 19C, but even in 12.1, we support histograms with up to 2,048 buckets. And let's hope that in this case, when we go with 2,048 buckets, we're going to end up with a histogram that has specific bucket for the values that we're after. Right? So if you run this, yeah, we have now 2,048 buckets, right? And if we check whether we have any buckets for these particular values, they have none. So we are out of luck, right? So one could say, well, how about sampling? Why did sampling didn't kick in? And well, sampling, there are also some rules when sampling kicks in. So for these particular tables, we had a simple filter. We had histograms in place. So most likely sampling didn't kick in for this particular table, for this particular single table cardinality estimate. So what I'm going to do now is I'm going to force sampling for that particular table for location by specifying this hint. Let me see if I improve the cardinality, the single table cardinality estimate for locations, whether I'm going to get a better plan. So I'm going to run this query, and we're going to observe what will happen. Now, one thing to notice when you have large cardinality or cardinality underestimates, especially if you're running a parallel query, what may happen is the optimizer may choose to go with a broadcast distribution where, for example, a hash may be more suitable. The thing is, with the broadcast distribution, it thinks that it will have to broadcast 29,000 rows to every consumer. However, the reality is it's broadcasting 17 million. So overall, it's broadcasting, sending 66 million rows, which is another thing that may happen if you have underestimates. All right, so let's go now to and see the other. I have to move this again. Let's go and see this particular query where we have, it's still running. So it's taking about 50 seconds. This is the query where we actually forced, let me just do this. We actually forced, it's done. It looked slightly faster, about a minute. The previous one was a bit slower than that. So let's see what happened. Again, this is our SQL monitor, right? We still have these nested loops, but again, where do you start? Well, you try to find out where the activity is being spent, and the activity is, is spent again in table lookups for products table, right? After the data being accessed through an index. So, but one thing that we were after was addressing the cardinality estimate for locations. Now, let me just modify this a little bit so you can see it better. All right. So as you can see now, we have correct cardinality estimate. Remember I said it's 60 rows because we're using small table replication. We end up with 240. It's like broadcasting the data to every consumer, right? So you have 60 here, 700 here, and you can look at this cache join. The join cardinality now is off. Okay, we estimate cardinality of 20. The actual cardinality is 150. Now the thing is, once you start having big cardinality underestimates with respect to the joins, if you have multiple joins, that may kind of multiply itself and may affect the other joins as well. So here we have 200, 1500. Well, the cardinality underestimate ratio here is pretty much the same, but in general, that may happen. Okay, so now we need to understand why the optimizer came up with this cardinality underestimate. So again, overall the estimates are better, right? So here the estimate before nested loop join is about 500,000, but still the optimizer thought, well, I still think because of the size of the table, I still think maybe it's better to go with nested loops join and index lookups. Now we have again big cardinality underestimate, which is maybe about 30x, and now our goal will be to actually improve that and see if by improving cardinality estimates we can get to a better execution plan. Now, in order to understand why this particular join cardinality ended up, with this underestimate, we need to understand how do we do the join. So as you can see, we are joining the data on location ID, right? So let's go back to the query itself, right? So this is the location ID, and we have filters also on two sides of the two sides of the two. We have filters on both data sets. So filtering on L-city from locations, and we are filtering on store type. That can also influence the cardinality, the join cardinality. Let me see if I have now. Just a second here. Oh, I'm moving this. Okay. Oh no. Okay. So what will happen here is, imagine we didn't have any filters, right? You're joining two tables. You're joining locations with stores, and the join will produce some new data set of the joined rows which are joined on location ID. Now on that data set, we apply two filters, city and store type. I mean, in reality, that's applied before, but I'm just giving you a simplified analogy. Now, in order to estimate the selectivity and cardinality for how many rows from that joint data set will meet this criteria of these two filters, we need to figure out what's the selectivity of the one filter and what's the selectivity of the other filter. You kind of multiply them both. Now, what will happen if there is correlation between city and store type, which there is, right? Well, if there is correlation, what you end up with will be with cardinality underestimate, because when you multiply two selectivities, right, selectivity is typically lower than 1. That's like a probability. What's the chances that a row will satisfy this particular criteria? So when you multiply something lower than 1, twice, right, you have, let's say, 0.5 times 0.5, you end up with 0.25. So it kind of goes down. However, if you have a correlation between these two columns, then the actual selectivity may actually be even 0.5, right? So you end up with an underestimate. Now the question here would be, which I'm going to answer myself, can we create a column group? Well, if this was a single table and you have two filters on two different columns on a single table, then you would naturally create, or would like to create, a column group, which will tell the optimizer a bit more. Of course, if the data is correlated, will give the optimizer a bit more information about the correlation of the data. However, here we have a join, right? And the columns are from the different sides of the join. So we cannot create a column group, right? So I'm going to switch back to slides at this point. Let me just, right? So what do we have so far? Well, we have a case where standard statistics are not sufficient, right? And due to data distribution, the histograms are not effective either. Now, dynamic sampling helped us in this case to get the single table cardinality estimates right. However, due to the data model and data characteristics, the join cardinality is still inaccurate. Okay, so what do we do? Well, before trying to other methods, let's see what we had and how did we start. Well, and I hope this is not frozen. This is one of these things that sometimes Zoom may froze the presentation for a moment. All right. I mean, if this doesn't
build.
Well, I mean, that's it's not even. Yeah, we need to probably wait for a second here. This happens sometimes with Zoom. Now you can see my SQL developer window, right? Or not?
Yes, we can.
Yeah, but you can see my PowerPoint presentation, and you cannot see Safari window. Okay, because I cannot see them either. So it will be more difficult to explain it without the slide. Just wait for a second here. Bob, do you maybe want to share that?
Can you bring up the slide?
Where, so we can go through that, and then I'll go back to the, I hope this thing will stop by that point. Oh, I cannot even unshare now.
Look.
Oh, live demonstration sometimes. Oh, okay, hang on. I'm back. I'm still sharing. You can see my good. It typically takes a minute or two, and it really happens when you least expect. So what do we have? Well, what did we start with? Remember our original join tree. We joined locations and stores first, and that was first we had cardinality and estimate locations, and then there was a hash join with stores, and then we joined departments, and after that we joined sales. I don't know if you if you remember our data model, sales is our fact table, okay? But because here of the cardinality underestimates, we decided to join sales at this point, and then access supplier and access products with a nested loop join and using an index scan, right? Well, we call this left deep tree. So if you remember from one of the slides that Bob presented, what we want to have is what we call a right deep tree, where we access the dimension first and sort of prepare the joins to join the fact table. We access products, we access suppliers, then we join locations and stores and join to departments. Because we are filtering on this data set, we are filtering on locations and stores, we'd like to create a Bloom filter on the results coming from the join with departments between these two tables, and then push that Bloom filter down to sales. And then as we are scanning sales and applying the Bloom filter, pipeline the rows back to the the joins and actually perform the joins. We call this right deep tree. This is our desired execution plan. Okay, so what do we do now? Well, one typical technique that is used in data warehouses is denormalization. Okay, so here what we can try is to denormalize the join between locations, stores, and departments. For this purpose, I created a new table called departments_dim. We didn't mention, but these dimensions are not that big. Okay, locations has about 100,000 rows, as you already saw from the statistics. Store has about 5,000 rows, and departments has about 100,000, something like that. Now we are going to create the normalized table, which will contain the information or the data from all these three dimensions. So what we're going to end up with is a plan of this shape. Okay, so our query will look like this, where now instead of a snowflake schema, we have a star schema. Okay, so let's go ahead. Let's go back to our examples and see what will happen. Okay, if we run the query. So we have now we are joining to departments dim. Oh, 5 seconds. So now we are in that range that we are expecting, as Bob said, 10 seconds or less. Let's take a look into the SQL monitor and see what happened in this case. Okay. So what do we have? We have departments dim with perfect cardinality estimate, 1500, right? Times 4, because this small table application ends up with 6,000, right? And we get nice right deep tree execution plan. Well, one thing to notice here is that, and you may ask yourself, well, why did we get a perfect, cardinality estimate here? Because we are still applying filters on 2 columns, even from the departments dim, right? That's because, we used sampling, and sampling kicked in this case and ended up with a better execution plan. Now, or ended up with the correct cardinality estimate, right? Now, the thing is with sampling is it's good when it kicks in and helps, but sometimes it will try its best to help and still may not come up with a good cardinality estimate. So our imperative should always be, our goal should always be to actually provide the optimizer good information so it doesn't really rely on sampling. So let's go and disable sampling and see whether even with sampling disabled, we are going to get a good execution plan. All right, so the query is running and it's still running. We got a different execution plan. Now, some of you may know what to expect. Sampling is disabled. Where our database time is being spent, again, table lookups from product. Okay, so what is going on? Oh, cardinality estimate for departments dim is 8, actual, remember 1500. Why it is 8? Well, it is 8 because we have filters on 2 columns, okay? Remember what I said earlier, if you have a single table and you're applying filters on 2 columns, you may create a column group, which we are going to do next once this query completes, and see if that would help. All right, this is done. We're going to create a column group on city and store type. Those are the columns that we are filtering on. Right? We just get our stats, and you can see now that we have this funky column name that starts with C's. That's our column group. And now sampling is still turned off, 0. And let's run our query. Hopefully it completes in 5 seconds. right? Great, okay? The power of column groups, all right? So if you go and look into the SQL monitor now, you will see that the cardinality estimate for departments dim is pretty good. Right? You know, almost 1,500. Okay, so the problem is that at this point, let me just go to the slides again. And by the way, you have, you know, all this analysis here in the slide deck, right? The problem is that now we enter kind of what we call the art of finding excuses, right? Because we introduced a change in a way, a code change. We get all sorts of pushback. Like, this approach requires schema changes or code changes. We need to change this and that. If we change the code, we would have to test it. Like, well, of course, yeah, you have to test it. Or excuse like the person who developed this code is no longer with the company, hence no one can touch this, and so on. It's third-party application. And again, some of these are valid excuses, valid reasons. So what do? What if I tell you that you can actually address the problem without changing your data model or without changing your code? Well, you know, this is where we want to go and start talking about materialized views. Traditionally, materialized views are used to materialize expensive joins or to use materialize expensive aggregations, right? Some key properties here are the rewrite capability. So if you define a materialized view as query rewrite enable, what will happen is when the optimizer passes a statement, and if it sees that there are tables that are joined in the same way as they are in the materialized view, and columns that are projected in the query are also available in the materialized view, if materialized view is not stale, it may actually use the materialized view, the result from materialized view, instead of performing those joins. Yeah, pretty cool, right? So that's what we're going to do here. We're going to create a materialized view on the join between departments, locations, and stores. Pretty much the same thing that we did with the denormalization. However, now we're not creating a new table, we're just creating a materialized view, which will have a table. That's how it's implemented, right? So in this example, we don't use the MV for law aggregations, or we don't use the MV to join, the fact table, right? The MV refresh will be actually sub-second. We are joining 3 small tables. We use the MV to improve cardinality estimates. Okay, so let's go back to our demo and create the MV. It's created. It took like a second. All right. So let's run this now and see what will happen. I have a couple more minutes, so we started a bit late and a couple of glitches, so hopefully you will understand. Let's go back to our SQL monitor. This is not our execution. This is our execution, still running slow. Okay. So the MV refresh kicked in. This is our original query. Here it is. No changes, no departments dim. The MV rewrite kicked in. However, cardinality estimates are still off. What do? Well, same problem as departments dim, right? We created the MV, we gathered basic stats, but we didn't create a column group. So what we can do here is we can actually create a column group on top of the MV. Well, first we need to wait for this thing to complete. And while doing that, okay. And by the way, sampling is still 0. Otherwise, sampling would have kicked in and might have fixed the problem, right? So, you know, often I'm asked a question: how do you notice if there is correlation between 2 columns? One thing that I typically do is I like to know the distinct values between for the columns, how many distinct values that they have, and then I'm going to get a count of how many distinct values we have if we concatenate the values from the two columns, like city and store type in this case. And if this number is close to distinct values of one of the columns, that will tell me that we have quite strong correlation. So in this case, it's kind of very strong correlation, right? So we're going to create a column group on the MV base table. again on city and store type. Cargo created. Let me just run this all now. Sampling set to 0. Now still the same query. Here's our query. Oops. Okay. 4 seconds. Even better. Let's go see the plan. Again, as you can see, all right, this is our plan, right? We have same SQL ID as the one before, same query, and we got the desired right deep tree plan, right? So, you know, criminality estimate for the EMV 1500, and the nice right deep tree plan, and we got the desired execution. So I'm going to stop here with the demo part and give it back to Bob to do the final remarks.
Thanks, Mahalo. Since we're kind of a little bit over time, I'm just going to share one slide here. Again, I think one of the important thing here, the lesson here is the journey that we went through, right? Of analyzing the problem, finding the root cause. Because once you have the root cause to the problem, then the solutions kind of may become more apparent, right? If you just guess, then you have no idea why something may have fixed it, and then it doesn't help you in the long run. So that's kind of where I wanted to just end this presentation, and we'll take questions offline.